Good afternoon to all. And before my speech, I want to thank Mr. Mohammed and Kashif because they explained something related with my speech, subject, and maybe I'm not talking about the 2 hours, maybe 1.5 hours it will be long. And what's the microwave cavities, starting with these cavities? But it's microwave cavities, because if you talk about the teeth doctor, dentist, also say some cavities in your teeth. Cavities not as empty space, or laser cavities is also resonators, but at a high frequency. The microwave cavities is 100 kilohertz or less than to many gigahertz cavities. What is that? The definition of cavity is a space, 3-dimensional space covered with or enclosed with the conductor, metal conductors. That's also called, maybe the better one, it's resonator. If you inject some of the oscillating fields, then you get some resonances with their related modes. And the content of my speech is starting with the electromagnetic cavities. I'm going to talk about some simple cavity, let's say rectangular cavities, cylinder cavities, and after that, I want to give some information about the electromagnetic modes briefly. And pillbox cavities, maybe we can make some calculations related with some of the factors affecting the resonances or oscillations. And after that, we are going into the re-entrant cavities because we like it. That's the main cavity that we use in clystrons. Saturday morning, I'm going to talk about the clystrons, but at least a half hour of klystron physics has also been explained by Kashif, and thank you again to Kashif. And quality factor is one of the figure of merits of the cavities. Skin depth, another one. The problem, multifacting, Kilpatrick relations, and others, I don't know. Let's go further. Oops. And I have defined what the microwave cavities is. You can, at the right side, some of the cavity types or shapes. It's the coaxial cavity, made up of coaxial line, both ends closed, and the small piece at the middle cut to produce a capacitance. This part is the capacitance of the cavities, and the wall of the coaxial closed. And this is also similar to that one radial cavity. Tunable cavity, we are going to talk about the tuners also. And there is the toroidal cavity. That's the, I think it's from CERN. And elliptical cavity mostly used in accelerator. So in CERN. And let's look at the difference of the Laminar cavities. And we have many solid-state electronic parts. And why do we use it? Because the frequency range is different for the electronic pulse. And the electronic circuit has a kilohertz, some gigahertz. You will see in the klystron also what's that. And there's the gigahertz, tens of gigahertz, about 100 gigahertz. You can obtain anything. This is LC tank circuit, but what it is, it has inductance and a capacitance in the elements, but the geometry also is functional in the electromagnetic cavities. Relative losses due to conductors. Other means is resistance is in the microwave cavities is surface losses. And size, you know that one, Q factor, it's about 100 to 10,000 for the conductor is normal conductors, but superconductor is different. Applications, that's one, you know, everything design basis for most oscillator is LC circuit that we have talked before. And the other one, the microwave cavity is distributed field models. You solve the Maxwell equations, you can do anything. And again, the same questions, why we need microwave cavities. It's also energy store. It's possible, that I said before, is resonator. And the strong electromagnetic fields can be deposited in here. Frequency selective and filtering is also possible. It's used in particle accelerator and the amplifier. Efficient power transfer in the cavity and also standing wave formation. And what's the standing wave formation? One of the example, I think it follows, you know, everyday life. It's a microwave orb. It's a rectangle cut. That's some of the phase. You have a Electron, not a collapse. Magnetron injected the power into that one. The length of the microwave oven is a lambda over 2 multiples of. And the microwave oven's wavelength is about 12.2. If you are manufacturing cavity oven, then multiply by 6.1 centimeter to multiple of 18.3 or 24 and something. And the third picture is related with is the standing waves. It is the mode of the resonances. If plate that you chicken, if you rotate it, some of the places only heated. If you turn it around, then all the area will be heated by microwave. And how do you find the frequency of that one? Is that if you make a construction, a resonator, or for example, then you have to match the LNC, conductivity, matter conductivity, capacitance and inductance should match with the dimension of the rectangular cavity or whatever cavity it is. Let's follow this page.
What is C?
C don't like. We should know capacitance. Capacitance.
Skip to C.
And this it's explained before, TM modes, transverse magnetic modes, chamber is like this, then these are the cavity of the cylindrical, that's our favorite one, because we are going to use in electrons mostly. This is and you see the electric field and the direction of the magnetic field. That's very efficient in electrons. And you see all of the components of the magnetic fields and electric fields in here. And finally, M and P mod numbers, you can find the frequency of this type of cavity. Let's go further. And this is the TA modes, transverse electric modes, the same thing that we have talked on one page before. You can read later on. And this is the pillbox cavity. Everybody solved this type of cavity. That's the introduction of the cavity tool. And what's it's on a cylinder. If you inject into that, electromagnetic power into that, it will oscillate. Because infinitely many modes in here, infinitely many frequencies. But due to resistance and some of the other factors, will mostly decay into zero as soon as possible. The one is the higher amplitude will be long life. This one is the main mode. We call it main mode or the dominant, or you can say. And Cash will show you that on you can try showing this expression. And one of the things related with all electric field lines cross the walls, not magnetic field lines. It's only loops around, because maybe you have to remember it from current loop in a copper. But the electric field must be through walls, and that's the you can see it from here, and the other components can be written like that, and this one is the frequency of the with lump elements. What is lump elements? It's approximately ideal capacitance and inductance of the system. This thing. But in real life, not like this. Yeah.
Shouldn't it be ER?
Yeah, should be. Yeah, I'll go check it later. And if you solve this in the cylindrical coordinates, try and some garbage, then something mathematics, you can find the solution in terms of the nth order Bessel function. You can always relate with the Bessel function because it's everyday use in electromagnetics, very of course in reactor too, but it's important in the electromagnetics. Let's go further, and I have written I write all the references in the up or down or relate. Oops. You can check all this one. Another one. And that's the solution a little bit further. And at the end, you can find the energy quality factor. What's quality factor? Quality factor is a stored energy or energy dissipated in cavity walls. Input and output powers. And this one definition. You can find it if you want to measure it. You can find by this relation to. And the shunt impedance, another most variable object. If you shunt impedance is increasing, power is increasing. And this is another factor is the geometrical factor for this and the solution of power dissipation, energy content divided by 2, then you're going to get quality factor. Quality factor is not easy because most kind of quality factor exists to define a cavity, the complex cavities. And other types, we'll go back to the quality factor later on. What is the coaxial cavities? This is the cavity that we are going to use in electrons. That's such a, I have explained a little before, that's a coaxial cavity, of course, and cut at both ends, and the small part as a capacitor in here. And that's the real coaxial cavity, re-entered cavity. What's the re-entered cavity? Cavity is a space covered by matter. Some of the surfaces go into the inside, you get a new shape. Similar to that, not like that one. It's the re-enter, the word coming from that one. That's the cavity of Phillips Electron, re-entered cavity, or coaxial one. Another one is the radial cavity, this one, for another purposes. But we are going to talk much of these on Saturday morning. Let's go a little bit. We are sitting in re-entered cavities, and maybe you think I have to solve these ones, and you have to think about the coaxial impedances. You know, coaxial lines is the characteristics impedance. That's the input impedance of the propagation. It's the coaxial input impedance. This one. If you put the Z0 into place, you can get input impedance. That's the final result of the inductance. It is here. The tangent beta L. And at the beginning, I have to say my story because beta, I take all the pictures and some equations from internet. I copy and capture it. And some of the notation, some of the symbols are different. And mostly I have pointed out which one is. Due to that, this is the phase constant of the tangent beta. And the result is tangent beta is this. This is the beginning of all of the, or the cavity of we are going to deal with. And this is the other one is the radial cavity. You can solve the frequency, and this is the C is the speed of light, and the capacitance and inductance can be calculated from here. As still, I have said before, quality of the cavity is not simple because there different definitions of quality factors. One of them, unloaded cavity. Other one, external cavity. Two simple things. And if they are talking about Q0, this the unloaded cavity means let's go to the definition first. The quality factor is defined as the number of cycles needed to dissipate the stored energy. It's it's mostly depend on the resistance and the conductivity. And you can write the loaded cavity. Loaded cavity, this one external, the cavity of the external input related with the unloaded cavity with Q0 inverse proportional to it. And that was the beta that we are going to use is a coupling factor beta. It's different from the tangent beta and not related to phase. This is the most variable parameter for in collections. A little further. And another definition that this, everything is the same, and the loss is directly proportional to the square of the acceleration voltage. If you take it and go further, then you can get the RQ ohms in here. Those are the different Qs. That's the total Qs. And it's the most valuable figure of merits of the cavities that we are going to use in the selection of totally. That's the definition of that one. A little bit further, if you estimate the cavity of the quality of the cavity quality factor, then you maybe follow the forward power and reflected power. You can do it with the some pickup, some pickup coupler. We are going to look at later, and this is the coupler picture. You should not be here, maybe later. Then, if beta is less than 1, cavity is undercoupled. If cavity is overcoupled, go back. One more. No. This one. It's coupling factor. Cavity is overcoupled if greater than 1. But we have to own beta is 1. Cavity is critical coupled. Then you can see there is reflected power goes to 0. If not, then impedance matching is not true. Then maybe the source will be damaged. And you can measure the Q also with 3-bandwidth method. You take the amplitude. If you use the VNA, you can find the frequency distribution. Then you take the sum of the frequency. I have to then get a motor. Okay. That's the measurement. Yeah, on the other side, you can cutoff frequency, lower and higher cutoff frequencies. You can find them here, such a formula. And one of the definitions, it's important in the design of the cavities and related with the frequency and the material, is the skin depth, is the depth of the electromagnetic signal attenuating in the material to 1/3, approximately 1/3 of the material will go into the material. It's about, let's say, copper about 300 kiloamperes. It's about 6 micron. But in engineering, you have to multiply it by 4. At least it should be 30 microns. If not, then your resistance will be high. That's the engineering share. In physics, it's only about the 6 microns. No problem for that one. But for good cavities, you should be 4 times of the skin depth. And the definition is directly related to the conductivity and permeability and the frequency. And the conductivity of the material, of course. Depends on the material and the frequency. If you talk about the vacuum, the mean 0 is the 1, etc. And the overall Q in here, is with a grid problem. Written with respect to their dimensions and the average over here. And extraordinary. And that's another concept in the you can choose the material like this. It's more storage. If you're talking about the quality of the cavity, then we have to know stored and dissipated energy. How can we calculate it? It's apparent, and it's also depend on the zeroth order Bessel function. That's the second line of that. One, if you put J0 into place, it's J1, something like that. Resistivity, conductivity, that we already know it. And fields, of course, in here. And it's okay for the stored energy. And this is the dissipated energy. You can calculate with this formula also. And this delta is the second depth that you have talked about. That is the approximately we can near to the full Q. The big problem, one of the big problems. And the other is also plasma, and due to that, the degree problem. Yesterday, some of the one guy talking about New Mexico. I forgotten his name. He talks about the Paschen curve. It is the breakdown of voltage in cavities or anywhere, not only cavities, but in space or the space or in the whole world. It's only for DC. And it depends on the pressure, gas pressure and gas entity, which gas is different. And but if you are talking about the microwave frequency, you have to think about once more the Kilpatrick, such a relation in Paschen curves. It's empiric stated that was about 1979, yes, 1987. And empiric stated that if you use this frequency at this electric field, then space will break down. It means you're going into plasma state. It's glow, not glow. It's mostly arc, and it's very dangerous, and all the things are collapsing. Think about the rocket launched from Earth to space. Let's say some of the rockets. You go into space, the pressure always down. At some point, voltage very small to break down. You can collapse all the rocket parts. And for this one is microwave, is also depend on the frequency, directly relate to each other. And you have to compute those things for your cat. If you apply some of the power, depends on the voltage, then the voltage cannot be high from this value. And welcome sparking. That's sparking one of the breakdown. And you have to be careful about that. And I couldn't agree. It's fine. That's the frequency. It's the AK. It's saturated. It seems saturating, but not saturated in general. That's the Kilpatrick relation. Of course, there is some brave factor. If you multiply the electric with 1.2, that's called the brave factor, but don't be sure about that one. Another problem, all those related a little bit, multiparting. It was explained before a little bit again. It's related with the secondary electrons. If some of the extra electrons related, and its resonance with the electric fields resonating with the same frequency, then you can go into the sparking again. This is the multiparting, and it's Mohammed was talking about the raising and such a cavities or such a the shape of the soundings is related with these ones. Then you have to aware of some of the specialty of the material that we are going to see one page later. One of that one is an example is the photomultiplier diodes. You remember it, of course. You have a photocathode. If a photon is straight through cathode, then will generate an electron. It causes the potential in diodes and strike it. Will be 2 or 3 or more electrons will be appeared and goes to another diodes and creating more electrons. That's the principle of the photomultiplier tubes. This is the multiparting. Some goggles, night vision goggles. It's also same multiplication number of electrons. If it increases, it will be the multiparting. And this is the, maybe you can read this one. This is the simulation, and we have checked it. Mr. Çiçek, he is now in Japan. Contract with the CAC, and write such a paper. And let's say some of the examples in here. This one is silver, gold, and copper, but not exactly exist for multiparting. Because the theory and experiment doesn't coincide. Let's see that now. This silver, if you clean it, optical cleaning, chemical cleaning, physical cleaning, not shown here. And these are related to each other. So gold is also, but a little bit different copper. It be different. And such experimental structure also gives some of the secondary electron emission here. Yes, skip the secondary electron. No, let's go. And one of the scientists gives such an explanation. This one, first order behaves like the electrons, it behaves like, and other than 3 more things. This is the secondary emission yield, and then the electric field here. And what is the secondary electron? But before the field emission. If you're very, very high electric fields, then some of the interfaces potential, one of the interfaces potential will break down. Then the electrons at the left will be tunneling. And that's another theory too. Or direct is electron tunneling. You can also check this one. That's the good references. And then another, the values for copper. Take that 100 degrees, not a big difference. I stored in memory. Okay, I don't know. Neon copper. If you make a coating on copper, titanium nitride or nitride, I don't know,
Right. See.
But it's is it same natural and inside the same?
One is in English, the other was in.
Yeah, okay. Thank you. Thing, but it's ceramic.
Correct.
Yeah. It's not a good conductor for electricity.
No.
No. Okay, and then if you use dielectric, then it's everything wrong.
It is,
Ah,
that should be a very thin film.
But
Titanium nitride is deployed on copper with the few nanometers thick.
Yes.
yeah, about nanometer, yeah. Even if about 1 or 2 nanometers. And it's impossible to simulate in CST. Because I told a little bit lies from home.
Is it possible to make in CSC program?
1 nanometer is not possible.
Not.
By physics. I'm not sure. Okay. But somebody is talking about overtime. I'm not sure you have. It's not a Victorian called. It's time. Few time. At the first try, all of the anode and cathode will collapse. I will touch you. And also it's a good comment. Okay. Can look at these papers. As said, actually, in fact, I have to talk about the CAY before the more paper, because it depends on the secondary electron yield. That it means secondary electron yield. One more author. If you secondary electron is the generated from another electron. If you strike some surfaces of metals, you can take it with 1 electron. If it means the energy of incident electron is greater than the work function. That's the definition of that one. And this is the one experiment related to this one. It's easy. You can do it if you have some abilities, physical. And these other references. It's the code. And if you characterize cavity, then you have to make some calculation. You have to know about the some of the units or figure of merits. It was the transit factor has already been cashed. And the shunt impedance is the up shunt impedance higher, and then the power stored is higher, and RQ only related with the geometry. That's one of the components of the softwares to simulate the collections, and also the loss factor. Most of the time, if you give the dimension of the cavities, then most softwares calculate, compute more of the, let's say, the RQ and other something, and Q factor too. Couplers, no problem. This picture is famous, I think, because the one that show us. Oh. And yeah, we talk about the empty space caused by the metal. How I can get to the, how I inject the power into the circuit. Then we need some couplers. And one of the main components. One of the things of these lectures, I have to say at the beginning, and Saturday morning, I want to force you to let productions. Most I am related with all those things. I define my ability with experimental instrumentation, blah, 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 blah. And I have to show you how to make design. Of course, it's just introductory level. So I've made some products. And of course, it's cannot produce smart. And most used one in low power. It is the first one is the loop coupler. You put a coaxial line and loop. Another one, electric. Electric. The second one. No, only magnetic loop coupling in here. Mostly known as a magnetic coupling. Let's say only one loop you have to put into the cavity. If you put into the cavity, it also have a volume. And
Hocam,
yeah,
may I ask you something?
Yeah.
When they're in that magnetic coupling,
Yeah.
Why the antenna is just one loop? Why not more than one loop?
you can do it another, but then the inductance will because I talked about the Qs. The input impedance should be Z0, and we solved the ZI. The impedance is impedance. It's very
So we need matching, impedance matching.
because ZI will be different. And one of the photo that we have showed before, a loop in a cavity. Maybe we can. That's the real one. We are going to real world from the computer world to real world. This one is from the computer screen, and of course we need it. And this one is the components, and this one is the produced one, and this loop is in the cavity. What's that? Oh, it's another one. And this is the copper, oxygen-free copper. We are going to talk about it later. And this is the coaxial line. This part is in part of cavity. This cavity is an RFQ proton accelerator. Another one, this another coaxial line going into bunch cavity. It's also the loop. It's a magnetic. I'm not sure. It's Phillips cluster. It's also the input of the bunch. And this one, I couldn't see for me. This one, all those things in here. But three couplers there, two couplers, and the whole T size. that is the measure, the transmission and the reflection of the power. Reflection must be zero in ideally, but it's impossible in real life, but you have to measure it. If the reflection is low, then everything is good. Impedance will match. Otherwise, unmatched, and the problem arises. Okay, that's the magnetic coupling. Let's go further. And that's the probe couplings or electric coupling. It's on an antenna. They radiate into cavity or waveguides or whatever it is. And you can design it very well. If you have a, maybe in electromagnetic lab, you have to see small electrons for to expand oscillation and waves lecture or course. Maybe you have seen it. If you open some small cavities, you can see at the end of the cavity. This behaves like that's the field lines, and then how to make it. That's the dimensions, sizes, but it's also important. And this is the low power. That's high power one. We construct such a one about for 352 megahertz, about that. And that is the pulse compressor input. One of the company has built it. It was Ankara University. I'm not sure where it should be. And another one, most used for high power, extremely high power, slot or aperture coupling. All of these three can be used for input and output. And this was again, the output coupling of the Philips Electron. And of course, you have to compute those dimensions too. And it is I think so. It is the alumina at this side, and this is in vacuum. This is going to then at the time we have shown that is, and measuring all of the things, we decided that this cholesterol is about 1.3 gigahertz, because you can find it from the cavity sizes and the slot also. Tuners are filters. This is filters, and this is the resonator and the coupling loops, and it's obvious it is magnetic loops, and this is the such a cavity. Which one? Radial cavity, right? And this is the and it's a real part of that one, real photo, and this is what the cavity with plunger, but pistons. If you press the pistons, then you will lose some of the volume, and the frequency will be changed. And of course, you can take it out, then the frequency will be high with respect to their sizes. And this is the tuner that we have done. and the number of it is about 16, 1.2 meter cavity. And one of the my preference is to clean the cavity and to make a high voltage or a high power conditioning. We use plasma. You see, this is the extension of the one of the tuner. Normally, such a cavity can be conditioned as more than 1 month, at least 8 hours a day. But after, that's a quadruple cavity. It means you have 4 sections. For each section, we have charged about 3 hours. And finally, up to 85 kilowatts, this was done in a week. I'm not sure. Maybe it can help to multipackaging, because we observed that plasma, some of the small hot spots appeared, and maybe small coppers will disappear by heating and something else. I don't know. But it's important for us. Okay. And why this is collectors? Yeah, we are still talking about the components. I'll skip this one. I am going to talk it cholesterol.
Excuse me.
Yeah.
May I ask a question?
Yeah.
Okay, you mentioned about the oxygen-free copper. Is there any level for sensitivity for this copper, and you check the sensitivity?
Yes,
and
maybe 1 or 2 pages later, I am going to talk about heavy oxygen-free copper.
About 6 and also within 6 and 0.9999.
No,
Yes, the purity.
1.02. Purity.
Yeah, purity.
I should oxygen now.
Should be
Conductivity is higher than 1 with respect to the other composition.
yes. Also
Other
oxygen, you know.
Yeah, less than 0.001, etc.
Yes.
Maybe written there. I'm not sure. We check. Why collectors? Okay. Collector and others again here. At the right, you are the Phillips collection. We are talking later. I confused something. My computer is not here. I have received it about noon. I forgotten it in Ankara. Okay. I'm not sure. Maybe someone has changed it. I'm not sure. Yeah, oxygen-free copper. It is the most conductive copper. But because we have shown that the quality factor depends on the surface resistance, it means the real part of the complex resistance. If it's resistive, take it out. This is around 1 or 1.1% conductive with respect to others. Why don't we use silver or gold? Because it's very expensive. That's the most conductive material that we are going to use due to that prices. And yeah, content is about 99.99 purity. And maybe
Did you check it, the lower content? test.
Yes, of course, but oxygen is very difficult to measure with regular spectroscopy.
No.
But
ICP can be used. ICP.
ICP, I'm not sure because it should be how to spray the
We did
copper.
it, you know. Yeah.
You
we,
did?
we did, yes. We measured oxygen.
Extremely difficult. Extremely.
No, we have ICP equipment here, you know, we do it.
Ah,
Yeah.
I don't know. I am not good at this.
Yes.
ICPs and
It's
some
actually
chemical
saying,
things.
you know,
but
oxygen content in copper, you know, we did.
It's very difficult. I'm not. Okay. Now, and it's mostly known as the American standard C101. You can read on some spectrometers, but actually it's C1000 and oxygen-free enhanced copper. But if you want to buy some this copper, they ask some questions. What about the percentage of forging? In CERN, I have the guys from CERN, they told me that you have to buy it with 20% forging. I knew shit. Okay, but everyone, the result was very good. And the other one is C10 200, C11 3 zeros. It's a little bit different purity. It's 99.95 C10. Another one it is American standard. In UK, Europe, and and Japan, standards are relatively equal. And okay, yeah, 10 ppm oxygen. Okay, but it's 1130. And at the upper right photo is the copper that I have bought 12 years ago. It's about 1.6 ton. And we use all of them. And the price was, please check price. It's offer prices in the international stock. It was $5,000-6,000. It was, but I'm sure it's more than 120
Per kilogram
No, all of them.
for the entire.
Yeah, this packet. 1.6 kilogram. No, ton.
Ton.
Yeah, ton. To 56,000 ton. Then it's over more than 100.
From China?
No, from Italy. Because Sun does not use China material. They bought from the Italy.
This is oxygen free.
Oxygen-free enhanced.
Forming copper.
Yeah. Yeah. That's the product that we have done. Cavity. This is the radio frequency quadruple cavity, proton accelerated cavity. And then it's 1.2 meters. Sharm RFQ core is about 3 meters with 3 pieces with 1 meter coupled together. But it was the first try of us. There were no stuff related. This one. Because of that, I'm going to push you into here. Push make a cavity, whatever it is. It should not be accelerated. It should be magneton. It should be Electron. But the problem is to be in relation in industry, in relation with other people's. And all of the stuff, except one or two people, is only no theory. Everything in life is ongoing on computer security.
New generation.
Yeah, that's right. The most of the generation making something before 80s, 1980s, before computer. But of course, it's very easy to make a simulator design with computer, but imaginable, yes. I'm not, but my brain pushes away all the programs and all the, I don't think make anything with the computer program. But I'm going to analyze everything. And it's also a different ability, but you have to touch your material, you have to touch it, you have to mix it, you have to carry it. I don't know. Yes. Okay, let's go. This is the CMC at the upper side about the 6-axis. What does 6-axis mean? 6-axis, freedom. And another one at the right side, the bottom, wire EDM. You know EDM, what does it mean? Electrically discharge machine. And it's cut by plasma underwater. And this wire in industry, in a normal cutting, is about 100 and 200, or mostly in 150 microns. But I know, I see, I can't see, of course, 500 wires, 5-micron wires in thickness. This technology known as non-tolerant technology, because how do you know, how do you make such a magneton cavity? Such a magneton cavity. You have to use this one. Okay, let's go. One page. And brazing. You have to talk with Mom. I asked the filler material because I want to be informed, but I'm curious about these things. And this is this one. The small flash. 304 stainless steel and copper, and the other side is such a ceramic. I think it is aluminum, more than 99%. All those things are on 20 centimeters, not much more. It's $600 if you take it to April. And this is not less than $300 or $400. Some of the guys or ladies here in ceramics say, yeah. This is the example that you are going to burn many dollars. If you make a brazing, you can sell all over the world. It should not be carried. It should not be accelerated. This is the technology. But you have to make a brazing. Mostly, if you are using copper, then you have to make it vacuum. And you need the most problematic one is to make brazing between copper or metal and the ceramic. Metal to metal is easy, and you have to choose convenient filler material. What's clear? Filler material. Let's go. Oops. Let's go further. This is the filler materials. You know welding? Of course, you know. Some wires and some, yeah.
Sort of furnace you use for brazing?
A lot of about 1,000 degree.
Level of vacuum?
Up to 7, up to 10 to 7 talk. But it's 6, it's okay. Maybe I'm sure it's 5 is also okay.
Okay.
No problem. Due to the oxidation, everything related with the oxides, mostly.
So graphite type vacuum or some molybdenum type? The heating element.
Heating elements mostly tungsten. Because generally in an industrial vacuum furnaces, it's about up to 2,000 degrees, and you have to use. But the problem is not the heat. The problem is shielding, heat shielding. Most metals related with this one about 1,040 or 100. But some of the works will be have them at about 1,800. And all the materials will be grit. This is the of course we have connect most of the metals with welding, and you know all of the and TIG welding, arc welding, and another one. It's arc welding. Your metal will be higher. Will heat it to up to 4,000 degrees instantly. Of course, the oxide will melt. And brazing is less than 1,200 under this value. And soldering, you know, soldering. If you take iron and make a solder electronic compound, if you lower down 400 degrees, it's soldering. If you about 400 to up to 1,000 around this, it's brazing. Another one, the welding. Do you want to make a filler material for brazing? No. Let's try. Do you have a time or?
Yes, we can. You continue more?
I'm not sure. This space, I'm not.
You have time until 5:30.
5:30. It's over. Maybe we can just take a break.
Break.
Maybe I'm not sure.
We can finish
after-
earlier. No problem. I mean, if you finish earlier, that's fine. If you finish at 5, that's fine.
Let me check that. I don't know how to pay genre. Let's fish. And maybe 20 or 25 minutes. Yeah. It's okay.
Okay.
We don't have any oven now. But if you have a material, an oven,
Wire bonding is a kind of welding.
between welding and soldering. Brazing, if you're talking about the brazing, we are talking about the welding and the soldering. But mostly I'm related with ceramics and metal, especially for copper. And of course, it's valid for the copper, and copper other things. Brazing one advantage. You can bond two different metals, but it's not every time possible in welding. You can not weld with copper with aluminum, let's say, or other things. That's three metal. And maybe you can, I'm not sure you can see it's the upper part is there, white. Other one is something gray or black. The upper portion is the TBAE, polyvinyl alcohol. Other one, the bottom one is a three metal: copper, silver, and titanium. Pure titanium. If you mix it, no. Great physics in here. Mixing is a great physics subject.
Homogeneous mixing is possible.
Of course, possible, but you have to make many process. After that, after trying this one, I learned that one.
Particle size also again.
Particle size, particle weights, and everything is possible. And maybe in 1970s, two physicists to make a good mixing of antibiotics, 3 or 4 day or 1 week antibiotics. There are different sizes. If you shake this one, different materials, the big ones goes up. But it should be homogeneous. Okay, now that's the out of subject. And the real material with 3 metal, titanium is the key element to wet the surface of ceramic. Wetness is another physics subject. If you do not, you will make not a wetness on this one ceramic, you cannot be born.
Raise. You can.
Yeah. And okay, let's assume that everything is good. Next. Now what's the TBAE here? It's no chemical property. Wow. It's a binder to make a cream. PVA soluble in water, of course, in hot water. Let's put something here. All of these about the 5,000 Turkish lira. You can find every material in Turkish online store. The advertisement, but if you're another store, you can find but the dimension is important. You can find convenient sizes. Okay, of course, yeah. No. Let's put some water, but it's cold.
You will drink it such as manna.
Huh?
You will drink it.
I'm not sure about the result. But you add some more. It will be mud. And after, if it's enough amount of TBAE in it, it will creamy-like structure. You put in a injector and press the pistons, and you put somewhere here, or you take with the gloves, of course, you can put and take a finger and put somewhere else. And you can spatula, that's all. After putting these material into places and take it out to vacuum oven. And of course, there exists some process should choose
Sorry.
yeah.
What is the material? Copper, titanium. It was copper, titanium, and
Copper, pure titanium, because if you say titanium in the industry around locally, they give titanium, aluminum, vanadium alloy. And this is the powder. It should be, it depends on the powder size, it depends on the distance between the materials to be bonded. And approximately 100 microns and 150 microns, because I have bought copper, I couldn't find. It's nanometer copper. You will the result now. You will see. And okay, we will do whoops. And of course, you need a vacuum pump, vacuum ovens. The right side one, I'm not sure who is the owner. The other countries, and at the right side, at the bottom side is a Turkish one that I designed and constructed for arc plasma coating. And the diffusion pump also is our design.
What is the size of this vacuum furnace?
Upper one or lower one?
Both.
This one is about the 1.2 meters, around 1 meter cube. I don't know the upper one. It's same, I think. I'm not sure. And the diffusion pump is also our design. Multiplied by our prices with 50, then you can get the price of this one. Okay. I'm going to skip this one. You can read later on. This is the result. Not the result. This one is ready put to the oven. This is the oven that we have used. And that's one of the results. The ceramics will be broken due to the some expression, error calculation, some erratic calculation, because the copper was extremely expanded. And you have to make some geometries and to escape such a. But Those are the others. I have checked all of them with the helium detector. I have to ask a question to Mohammed. I'm not sure. I can't see which material which. And this is the aluminum or something else. Maybe. I assume that is aluminum. I'm not sure. And that's the result. I've checked also the vacuum type. And another try, this one. This is solder. I have put here copper coating and small PVD chunk. It's Cavities, small can, glass can. It's PVD is a very simple thing, and if you put some copper type in here and you make some coatings on the ceramics and make a solder. If you make one piece, then you will not need any oven. Oven price, that's the other countries brand more than $500,000. You take two, then it's $1 million. Okay. And how do we use some of the softwares to design cavities? It's, I don't know, I'm not expert on this one, but many of them. What is superfish? Superfish is free. And this one is, I know, of course, but it's very expensive. But many of you have, maybe student version is free, I think. I know a little bit AG-Disc because we started the design, the Electron design started the AG-Disc. And maybe you know the other ones, I don't know. And yeah, it's superfish mostly used from some people to make a pre-design with this one. And this is at the right side is the you can download from the CERN site. But one of our friends, the young friends, there's Nur. And then this surname is Meta, but changed into the English name. He's married to an English guy, and now is living in England, in London. But I remember their surname. I'm not sure. But if you, yeah, it may be in Manchester or Cockcroft, maybe in there. I'm not sure. It's right something about Turkish. Maybe you read it, or you can download the other English version from the CERN site. Superconductive cavities, you know what it means. The resistance is zero, not zero, of course. It's next to zero for DC fields. For AC fields, is very, very tiny. It means when losses are very low, Q is very high, then it means the ability of storing energy very high, and high quality factor. And you can, and then the high field gradient is very high. It's about 30 million electron volts around. And continuous wave operation possible. Okay. Of course, key differences for normal and superconductor cavities in here. You can, wow, the big problem. Temperature. Normal conductor is room temperature. But for superconductor, sometimes it depends on the material that you have to cool down. Let's say, did you see any superconductor? Yes. Yeah, okay. At the middle of that is a superconductor. If you want to make maybe see you later. And about 2 kelvins. It means you have to lower temperature by, firstly, by liquid nitrogen or liquid air. After that, you put the liquid helium. It is a big problem. It's my opinion.
Are superconductors suitable for this? Maybe machining might be difficult, right?
Machining is not a machining in general, because they are making statically isostatic press or mechanical press. Let's say niobium is a very soft material, and you take it as a plate, and if you make some molding for the shape of your cavity, then press it. But some welding moldings, not freezing, you have to weld that, then you need vacuum again for electron cavity. And if you're operating in, you have to supply continuously helium, liquid helium.
I mean, for type 2, like HIPCO, nitrogen temperatures becomes a superconductor, right? Is it possible to
No,
machine?
I didn't hear anything about the nitrogen temperature. Superconductor, any superconductor in nitrogen temperature.
It's nitrogen 70 Kelvin, 77 Kelvin. It becomes superconductor.
I'm not sure. I'm not
nowadays, but I thought it might be difficult to machine, or
I think so.
those things will be problems.
Of course, yeah, you are right, because many of the, all of them, not all of them, it's because
tin metal always.
Yes.
this is the only flexible one. That's the cable surrounding
It's
surround.
wire. It's
It's wire. Most of them surround. If you make a small stress element, just it will be cracked. Maybe. All right.
Otherwise, it would be very convenient, like you can make
I think so.
superconducting cavities.
Yeah. Thank you. That's what.
What about graphene?
I don't know. Graphene is a superconductor? I
They're
don't know.
saying yes at the root.
What is that?
Not superconducting, but very good conductor.
Very good conductor, of course, but it's
Well, I know something that's achieved the superconductivity with graphene. But I don't know.
we are talking
There's
about
no-
the
Yeah, I heard,
conduits.
I don't know what is the ship.
And there's also, breakdown current, also breakdown temperature. Because, you might have a superconductor, but the
clear
current,
also.
it may not,
Yeah,
it may change phase,
Yeah.
That's another thing.
Magnetic field also is.
Magnetic field also, yes.
I don't like the superconductor. To make it such as I am old man, and I am very conservative. I like copper, and I don't like super helium, liquid helium, the nitrogen. It's extra problem. Okay. And we are going to talk about, they were explained before. And if you fill in the, maybe you can remember that one of the problem arised about 10 years ago. I'm not sure. In summer, to heat up to room temperature, it takes about 6 months. And after repayment, to cool down it, another 6 months. For sure, you know very well it, yeah? I remember. It's a big problem. Yeah. Okay. Iran further. And still materials and the history and usage a little bit. And of course, there are some references there. Anybody knows, is there a superconductor cavity in Turkey? You know.
It's a cavity.
Anybody else?
Nice.
In Ankara University has some facility in Gölbaşı. Where you know Tarla? Where are you from, Tarla? Because you say Tarla before.
Yes, we have a collaboration with the laboratory and we did some.
They are also in our technical committee.
Really?
Machine advisory committee. Yeah.
Super. Ankara University and 6 or 7 universities more make an association to make a facility and make some accelerators. But they choose superconducting accelerators. Of course, it's the problem. I don't know. This is the tank, the cooling tank for superconductor cavities. Another one at the right side is the, you see, air liquid. It means, of course, air means nitrogen. And at the bottom side is the helium tank. Produce these liquids form of these gases to cool down the cavities into superconducting state. And maybe another superconductors in Turkey, I don't know. I would know, but no. Yeah.
You mean to super cavities use materials?
Yeah.
Pure niobium, nicer test cavity. Am I right?
No, I think so, because I'm not, I don't like the superconductors.
Because I visited Tavra facility twice.
Oh.
I was there.
Okay. Maybe if you go to Gölbaşı in Ankara, you have to visit. They are very friendly. You can visit everywhere on there. Is there any person here?
Are there other people working at Tarla participating?
You are staff in Tarla?
No. Staff member from?
No, I'm student at same building, Ankara University Institute of Accelerator.
Yeah, that's the, but your student at the next building. Yeah, right.
So so I visited twice.
You have to visit every day.
Huh?
You have to visit every day.
Yeah.
At the next door.
Yeah. Actually, I couldn't visit every day because.
Of course, I know. It's jokes. It's just joke. Okay. Okay. Aha. and I'm not sure. It's the Turkish biggest cavity ever made, but I don't know it's true or not. That's the cavity of ours in installation state, and it's a 1.2 meters and RFQ proton accelerators. And then it's produced in this company. And the last stage is the video. I know about it.
For what energy it is designed? How much energy you would get from this cavity?
Energy for input, output energy,
Output.
1.3 MeV.
Current.
It's about it's 1 milliamps output. Why? Because all of the most outputs of the RFQ accelerators over total milliamps. Let's say CERN RFQ is about 55 or 80, but they are professionals, and the same beam group is the stuff about 52 members. And the money raining into CERN, but it's not common for us because many engineers and scientists will couple with us, not with me, of course, because I'm out of this world. But due to that, I'm going to push these people into production and design and production, of course. And this is the good days for us. It's about 2019, and all the people talks at the same time like Italian. Why we did this? To gain experience. One component that we have out of local tetrode amplifier, and I'm going to talk about the next. I'm going to talk about the cholesterol Saturday morning because I want to make cholesterol instead of heteroton 5. And with the only component that should be changed. And after that, we are going to make more accelerators. This is my dream to make electron for heavy carbons. We have done it, right? It's important. How many electrons such an accelerator in Turkey, you know? No. Only 56 at board. Total around 250, I think. Maybe you have to check from the 10 mark records. 10 mark. Please watch this video. That's recommendation for you for Saturday morning. It's very, very explanatory video. It's a very simple. It's animation for cholesterol. Kashif has also explained everything. Thank you for that.
Thank you.
Okay, that's the end of the lecture.
I have a question.
Yeah.
You were talking about the plasma cleaning.
Yeah.
Can you explain the process a bit more? I thought it you nitrogen inside or argon?
Both,
Okay.
whatever you need, it's kind of you use the nitrogen,
This
but
color-
maybe argon is most suitable. I'm not sure. Most argon. Which one is the higher atomic number?
Nitrogen is least ionizing as compared to argon.
Yes, but you have to increase the volume.
Yes, sir.
And the curve should be about 10 and 15 milliamps. Maybe I can write the channel of that scheme for you because it's two dice structure.
And you have a continuous pumping.
Continuous pumping, and 2 or 3 hours for each segment. And small maybe technical enough was it?
I didn't do the plasma cleaning thing, but what recently we've been doing that we have a continuous flow of nitrogen whenever we need an intervention in the accelerator.
Yes, but the end we do the same because some power, nanopower, will be correct. Because the nitrogen or argon, iron bombarded, taking some copper. Let's say in either like reactor, yeah, 4 pounds of metals in the structure. Every year has to take it out. It should be out. You have to check it. You have to investigate it.
My question, do anyone design these vacuum furnaces? Replicate these vacuum furnaces in
One of the company system set up the node very well. Yes. You know, yeah,
Furnace, you know,
I don't know.
Monolog var. Furnace mi?
But the vacuum furnaces. What about the temperatures of the
We're aiming around 2000.
It's powerful. And 2000, the system was using also the tungsten ocean because of the chemistry. It's no lighting. But
I think that the most important part of the share of existing structure is only they will.
Another one thing, it's about 1040, 400 degrees. More TCM, titanium, zirconium, TCM, titanium, zirconium model then. But it's limited to 1,400. It's widely used in class. But about up to
One more question about raising, if you have three different types of raising same structure, you have to be 3 cycles of raising. And raising techniques. In the temperature.
yeah.
Every time you have to.
I forgot it. You have to choose 3 different of or 4 different of material. Then you can be start from 1,200 and at every 100 or 150 degrees, you have to down 4 steps or 3 steps or 4 steps.
These basically.
Everything, because there are receipts in the internet. I take it from the internet. Maybe you have to remember it. This is I'm not sure about this recite is I said I think 1.75% from weight, of course. Maybe 50% copper or 60%, around 40 or 38% silver. If you mix that's right. That's it. But actually, as I said, I couldn't remember the commercial nature. But you can find any size.